The last speaker of today is Antoine Jego, who's going to talk about Uniqueness of Malliavin, Kontsevich, Suhov methods.
Thank you for the invitation. So this is joint work with Guillaume Baveret, who used to be a postdoc in Berlin, and this year he will be a postdoc in Marseille with Rémi Rode. And this talk will be about infinite measures on the space of this talk. It will be about infinite measures on the space of Jordan curves in the sphere. So, Jordan curves, it's a curve like this. So it's, if you want, it's an injective continuous function from the circle to the Riemann sphere. There will be SLE type curve where kappa belongs to this range of parameter. So the range of parameter where the SLE is a simple curve. And they will satisfy some restriction property. And the question addressed in this talk is, does this restriction property question, does this characterize the law, this measure, the law of the curve? Okay, so I realize this is a talk, it's a talk in the continuum, maybe. But no worries, if you are a discrete person, I'm not going to use many advanced tools. Let me maybe just recall that when I say conformal map, if I have two domains like this, if I take a conformal map between these two sets, I'm just considering a map that is bijective, complex differentiable, and so that the inverse is also complex differentiable. And okay, one thing I will use about conformal maps is the Riemann mapping theorem. If I have two simply connected domains that are not the whole plane, they are conformally equivalent, so I can find a conformal map from one domain to the other, like this one. Okay, so what's the motivation behind this talk? Motivation, maybe? Or motivation one? So scaling limit of critical system. So we have a model, statistical mechanic model, such as, for instance, I will take the example of the Ising model. So I have a continuous domain like this that is approximated by a portion of a lattice, where the mesh size of my lattice delta tends to 0. And on each vertex of my lattice, so this is the same thing but a little bit bigger, on each vertex, I have a spin, plus, minus, plus, plus, minus, plus, something like that. And I have a parameter in my model. Okay, I'm not going to describe exactly the probability of configuration, but there is a parameter, the temperature, T, which is often written as 1 over beta, the temperature. And this temperature, so basically the two neighboring spins, they tend to align. And depending on the value of this temperature, if the temperature is extremely small, this interaction is very strong. And there is a phase transition in this model which is basically capturing, you know, if I had a magnet, I could stick it there, and if I warm my magnet, at some point, we will see that the magnet drops. And so this model is exactly talking about that. So let me put for boundary conditions here. So I will have a plus spin on the left, a minus spin on the right. This will be for T large. So there is a critical temperature. So if my temperature is very small, the interaction is so strong that basically the plus boundary condition here will propagate quite deep in the domain. And in the scaling limit, actually, you will see an interface that becomes deterministic. I have the same boundary conditions everywhere. Here, the temperature is so large that I have basically a gas of atoms that are doing whatever they want, and so I have basically no interface, or meaning that the interface is either very close to this one or to this one. Here in the middle, it's a mixture of like each clusters of plus and minus spins are quite small, so it's noisy if you want. And at the critical temperature, we have a nice random interface that is not deterministic compared to this case here. And the scaling limit of this guy is called SLE2. Okay. SLE3. SLE3. Okay, but so the mathematicians and physicists, they both want to understand such scaling limits. Physicists, okay, so there are several approaches, but one big success was via this thing called the conformal field theory. And so the idea behind that is that the scaling limit of this picture is supposed to be conformally invariant. Meaning that, okay, so what, in particular, what does it imply? So if I'm interested here in the value, if I'm asking what's the probability that a spin here takes the value +1, then simply by conformal invariance, so I have one domain with 4 real parameters. One real parameter for the boundary point here, another one here, and 2 real parameters for my point here. So actually, simply by conformal invariance, I know that this function is a function of only 1 real parameter instead of 4. So already conformal invariance gives a lot of constraints to this thing. But we still have some freedom. And so what physicists have understood is that if you try to understand how your system is that now if you don't take a conformal map that is conformal everywhere in your domain, but that is only locally conformal, meaning that there will be some region here where this guy is where my map is locally conformal. And so basically what I'm trying to say here is that my system is heavily constrained by the way it changes under the action of local transformation. And if you do something like this, basically you will manage to obtain differential equations that in the end will be able to give you the value of this function I was after. So that's, if you want, the physicist approach to this question. And now mathematicians, they have a very different approach to this thing, which is basically to understand this function via the interface here. And so, so this is a big success story thanks to Schramm-Loebner evolution. And so the topic, the goal of this talk today is to make a link, if you want, between these two things. So, okay. So of course, many people have tried to do this. In particular, what's already known is that partition function here on the SLE side, they correspond in some way to a correlation function on the CFT side. But I in particular want to emphasize that there is this work by Maria Gordina, Wei Chan, and Yilin Wang, which is simultaneous to our paper, which is also about this link. Okay, so that's the motivation. Now I'm going to talk about another motivation, if you want. And so for that, I just want to come back to the setting of chordal SLE. So, if you want, this will be a definition of SLE. So that's the original definition of Schramm. So I have a simply connected domain like this, and I have two boundary points, A and B, and I want to talk about an SLE curve from A to B. And so the definition of SLE is that it is the unique, so it is the unique family, so family indexed by kappa of continuously growing pairs which satisfy two properties. So we want some conformal invariance, and two, we want some domain marker property. Okay, so what does it say concretely? If I have explored a portion of my SLE up to time t, then what if I satisfy these two properties, the remaining of my curve will simply be an SLE from that point to that point in the remaining of the domain. And so by conformal invariance, I can conformally map this new domain back to the domain over there, and be back again to an SLE from that point to that point. Okay, so this is very nice. But so this is a dynamic characterization of SLE, and actually also, maybe let me emphasize that the value of kappa is not identified here. So the question, can we find a global static characterization? That's the question. So I don't want to talk about curves that are growing. I'm just talking about one piece of curve that sits on my domain. So one possible answer is the couplings with the GFFs. So I'm not going to say what this is, but actually these couplings, they give you a characterization of this. So for instance, the easiest one is for kappa equals 4. when you say that SLE4 is the level line of some GFF, this is a static global characterization. Okay, but this is actually quite complicated. Oh, yeah, and in a way, my answer to this question will go via the restriction property. Of SLE. So this restriction property was derived by Schramm, Loller, Werner. Loller is different from Werner. And here the couplings with the GFF. Sheffield Werner. No, it's not Sheffield Werner. Schramm Sheffield and Miller Sheffield. I keep getting this wrong. Schramm Sheffield and also Miller Sheffield. Okay. So here what I want to say is that these people that derived a restriction property for SLE, but actually they didn't say whether this characterizes or not the curve. And really this came just a few years after the inception of SLE, whereas this was in a way a bit more advanced and it arrived a bit later. So this characterization is a bit more elementary in a way. Okay, and so it's related to this Kontsevich Suhov conjecture that I want to talk about now. And so, okay, so this was for chordal SLE, and now I will talk about, my measures on Jordan curves over there. So we'll talk about loop versions of SLE. So why do I do that? It's, when you have loops, you have more symmetries, so in a way, the overall story will be a bit nicer. And also, okay. And also, you could argue that they are even more natural than chordal curves. So I'm going to define, to give a definition of what I call restriction measure. So let Cm be smaller than 1. So later, later Cm will be related to kappa via this formula. 1 minus 6 kappa over 2 minus 2 over kappa squared. And I need square root. But for now, Cm can be anything. Okay. Let nu be a Borel measure on the space of Jordan curves. So of the Riemann sphere. So this space is a nice space. You can equate it with the natural topology and so on. And so I have a measure. And so for any simply connected domain, D, I define the following restriction of nu to D. So nu D, D eta. So eta will be, I will denote Jordan curves by eta. Okay, so I have the restriction that I want my curve to stay in D. So a priori the curve, so here I will have nu d eta. So a priori the curve can live anywhere in the sphere, and I'm just restricting it to D. And now I have, I reweight it by something, which is this value of Cm here, Cm over 2, lambda star, eta, the complementary of T. Okay. So, I don't think I want to define this lambda star. So this lambda star is a renormalized Brownian loop soup measure. So of loops that intersect the complementary of D and eta. Okay, so you don't need to know really what this is actually for this talk. Another way of talking about this object is to say that it can be defined using a zeta regularized determinant of Laplacians in some domains. So, for instance, like it would be in what? I think I will compare this like in my domain D and also in the domain delimited by eta. These kind of things. The ratio of several of them. So it's a very natural thing. And okay, so I'm inside the definition, and so we say that nu is a CM restriction measure. So on the space of journal curves, if for all simply connected domains D1 and D2, nu D2 can be obtained by pushing forward. So F will be a conformal map from D1 to D2, and so nu D2 is the push forward by F of nu D1. Okay. So this definition is not too bad actually. I mean, I have this value Cm. I take a nice Borel measure on my space of Jordan curves. I define a weighted version of the restriction to D of my measure nu. And then I say that this is a restriction measure if my restriction measures, they have this nice behavior under conformal maps. So to obtain nu D2, I simply need to take nu D1 and push it to the domain D2 by any conformal map. So you see, this is an interplay between restrictions and conformal invariance. So that's why this property is called the conformal restriction property. Okay, and so the conjecture by Kontsevich and Suhov is that for any Cm less than 1, there exists a unique, so unique up to global multiplicative constant. There exists a unique Cm restriction measure. So this article was published in 2007, and since then a lot of work has been done in this area, and especially the existence. Existence is known. Existence, okay. Okay, so let me try to get this right. First, Wendelin proved this for Cm equals 0. Right, okay. Maybe I should say this unique measure will turn out to be what we call now the SLE loop measure. This is important. SLE kappa loop measure. I mean, at the time of the conjecture, they didn't really speak in those terms, of course. And kappa will be related by C via this relation over there. So, and Wendelin showed the existence of this first for Cm equals 0, so kappa equals 1/3. Then Benoît Dubeda. Showed this for Cm equals -2. Okay, I haven't written it. Cm equals -2 maybe? Okay, not sure now. Kentainen. Werner. For the range of kappa between 8/3 and 4, and lastly Jan for the whole range of values. Okay. And so now, now we call these things SL loop measures, and but actually they are not necessarily all equal. Meaning, this one and this one, they agree. They also agree with this one. But for instance, this one, okay, before our uniqueness result, I don't think it was completely known that it coincides with the construction of Jan, for instance. And so, uniqueness. So uniqueness. This is what we showed with Guillaume.
Just to mention, when do you also put uniqueness for Cm equals 0?
Yes, indeed. Indeed, uniqueness was known when Cm equals 0, and that was the only value for which it was known. And as you can see, so Cm equals 0 is a very special value, because then you have something which is exactly which satisfies an exact. You have no weight to put here to have your conformal restriction property. So it's a very special value. And it corresponds to kappa equals 8/3, which is also special. It's the uniform case. Yes.
Motivate a little bit the exponential factor with this Fabulous part.
Well, okay, maybe. So okay, so first of all, here there is a star because of a renormalization procedure, because I am on the sphere. If you were to consider the same thing in a bounded domain, it would be easier. You would basically not need to have the star. So for instance, for chordal SLE, what you would do is that, let's say that I have first my domain here, and I cut out some portion of my domain, and I want to compare the law of the SLE inside the small domain versus the law of SLE in the big domain, restricted to not hit this part. And it turns out that there is a relationship with loop soups, and so you will have to count basically the number of loops that intersects your path and this region here. And that's what this lambda star is doing. Okay. So why is this nice? So for instance, this characterization of Schramm of SLE is nice, but it's really like you are growing your curve from A to B. So one thing that is not clear from this characterization is reversibility of SLE, meaning that if now I start my SLE from here to here, I want to say that in the end the two curves I have obtained, they have the same law. Okay, so this is now known, but it was a non-trivial derivation, because as you can see, this characterization is really in one direction. With such a characterization here, reversibility is immediate. And we have a nice consequence as well of this characterization. I will not derive it for you, but it's a duality of SLE, meaning that there is. You can also consider SLE for kappa. The SLE loop measure, I can also consider it for kappa between 4 and 8. And when I do that, okay, let me try to draw a picture. I'm improvising my picture here. So now I have a non-simple curve like this. Okay, but it's still a loop. So this is SLE kappa loop for kappa between 4 actually, 4 and 8. And you can look at the boundary of the connected component connecting infinity. So I can look at this guy here, the outer boundary if you want. And so SLE kappa, it satisfies basically the same restriction property. This restriction property is also true for kappa between 4 and 8. And so basically you will be able to, from the restriction property of the curve, you will be able to show that the outer boundary also satisfies the same restriction property. But now my outer boundary is a simple curve, and so I have a measure on simple curves that satisfy the same restriction property. So here it's important that CM is invariant under right. And so what this means here is that actually this guy has to be SLE for kappa prime for 16 over kappa. 16 over kappa because Cm, the value over there, is invariant under kappa 16 over kappa. I started with kappa between 4 and 8, and 16 over kappa now becomes something between 2 and 4. Okay, so for instance, so this is a very from this uniqueness statement, this thing is just half a page derivation, if you want, instead of complicated papers.
For the reversibility statement that you mentioned,
yeah,
it applies actually to chords or?
It applies also here. If I have a simple look like this, basically reversibility would mean that I want to reverse the orientation of my curve. And this will basically saying that if I have a curve separating 0 from infinity, I will just want to exchange the rule of 0 and infinity. I want to say that my measure is invariant under this thing. And for this particular fact, what you will have to use is reversibility of the loop measure, but reversibility under the inversion. But this is just a computation about Brownian motion. The fact that Brownian motion is invariant under z gives 1 over z is a computation. Okay. So now I will try to say a few words about the proof. Okay, but yeah. The proof. Okay, so from this restriction property, so now I will take any measure, any CM restriction measure, and I want to show that this is uniquely characterized by something. So from this, I will derive some integration by part formula, which will then enable me to construct some orthogonal polynomials, which will characterize the measure. Okay, so I will do a nice toy model for this idea. And if you don't like SLE, I think at least maybe you can appreciate this thing about standard Gaussian random variable. So I want to, so I have x, which is a standard Gaussian random variable. And so the integration by part formula I had in mind in this context, so before I had the complicated measure on the space of Jordan curves. Now the measure I have is simply the law of this random variable in R. So now my space is simply R. And the integration by part formula I had in mind in this context would be simply the Gaussian integration by part, which reads as follows. So I have a prime here, and now I have no prime on F. I have x gx minus g prime x. Something like this. Yes. So that's my integration by part formula. And here, okay, so already here we see a lot of nice properties. So for instance, we can read the Hamid polynomials from this formula, because if I define h naught is simply 1 and hn plus 1, I define it via this thing here, is x hn minus hn prime for n at least 0. Okay, so these guys, they are called the Hamid polynomials, and I can apply my formula over there with. Okay, so what do I take? I want to take f equals 1 and g equals hn. And if I do that, on the left hand side, I have 0 because f prime is 0, and on the right hand side, I have expected value of hn plus 1 of x equals 0. And this completely characterizes my Gaussian measure on R. This is here I'm just computing the moments, if you want, saying that I know the value of on all my Hamid polynomials means that I know all the moments of my random variable x. So we will want to do something like this here as well. Is it clear? Okay. Okay, so how do we do that? So now instead of having R, we have a more complicated space. So first of all, we need to say what this means to differentiate in my space of Jordan curves. That's the first thing we want to do. Okay, and also so what's also important is that this construction of orthogonal polynomials in our context, it will belong to a broader framework of building a nice CFT framework for SLE. This is what we are doing here. And so differentiating in my space of Jordan curves, what I'm going to do is that I will use a local conformal map and perturb slightly my curve by this. And this is very much, so this is closely related to what I was saying at the very beginning of the talk, where I said that you have your system and you are perturbing it slightly with the local conformal maps. So this is exactly what we'll do now. But we want to do something like this in a very structured way, and the way we perturb our system will be very much related to some nice algebraic structures, and so this is quite important as well. Okay, so from now on, I will restrict my measures to the space J 0 infinity of Jordan curves separating 0 and infinity. And so what is, okay, so the Vit algebra, so this will be my first algebraic object, which is a Lie algebra. So it's the Lie algebra of Laurent polynomials vector fields. So things like that. Where this V is a Laurent polynomial, so it can have a singularity at 0 or at infinity, like two special points. And okay, it is equipped with the following Lie bracket. So VW, this is equal to VW prime minus V prime W. And there will be special Laurent polynomials vector fields that I will denote by Vn, which are simply minus Zn plus 1 dz. And with this bracket relation here, I simply have these relations on my basis. Delta Vn plus m. Okay, so what this means here is that I'm simply considering my vector fields on my with the Laurent polynomials as coefficients, and they satisfy special properties, these very nice algebraic properties, and so concretely what this means is that you are able to do a lot of computations with them. And so why is this related to what I was saying before? Is that if I take a vector field, then I can consider the associated flow, and this flow will allow me to perturb exactly my Jordan curve. So the flow phi t associated to V is simply defined. So at 0, I want my thing to be the identity, and if I consider the derivative of phi, I have V of phi t. So concretely, what this means is that I have my Jordan curves like this, and if I consider, so this is eta, if you want, and now I consider phi t of eta for t small. And this guy is a small perturbation of eta if t is small. Okay. Is it okay what's happening now? Or?
So T will, I mean, you wrote T is in C.
Yes, so this is okay. So this is an extremely important point. I want perturbations in two directions. I really want to consider complex values of t. I have potential singularities at 0 and at infinity. And so actually this means that if I consider any compact sets, so away from 0 and from infinity, I will be able to make sense of this equation for small values of t. And here I really want to consider small values of t because I'm interested in the perturbation around t equals 0.
So it's not, one shouldn't really think of t leaving all of the complex plane, but rather just the neighborhood of the original.
So this thing is only well defined in the neighborhood of my curve. I mean away from 0 and from infinity. And so if V does not have a singularity at 0, actually this thing will be holomorphic everywhere except in the neighborhood of infinity. And so that's really why. So that's why this thing is considering quasi-conformal maps that are not conformal everywhere. It's really thanks to the singularities I have at 0 and at infinity. Okay, so that's nice. Now I'm going to define operators that are, if you want, differentiations with respect to this guy. So that's the first claim. So there exists a dense set C of L2 of nu. So you know, so before I had f prime. So f was a function in, if you want, L2 of my measure in R. And so now I have I will have a function in L2 of my space, which is a bit bigger, such that for all V in my Vit algebra, and for all eta in J0 infinity, I have f, and for all f in my dense set, I have f. So phi t is the flow associated to V, phi t of eta. When t is small, this is simply f of eta, and I have corrections. So t LV f eta plus t bar LV bar f eta plus little of t. And I mean, if you want, this is okay. So I need to say that there exist. So this claim says that there exist things like this, and so my operators LV, they are LV and LV bar. There are endomorphisms of my space C. You know, this is just saying if I take a nice enough functions f in my space of functions, then I can differentiate in the direction V. This is really just what this is saying. So it's the analog of what I had over there. Okay, and so the first result is if you want this this relation with this nice algebraic structure that we had over there, theorem, is that actually these things, there are two commuting representations of my Vit algebra, and so what this is saying concretely is that I take two vector fields V and W, and if I take, so here this thing is simply the commutator. So this is LV composed LW minus the opposite. So this thing is equal to L VW, where this time this guy is the Lie bracket that I defined over there. So really what this thing is saying is that these operators, they behave very nicely, and so this is what we call a representation of our Lie algebra. And the same with bar, and they are commuting. Okay, but so far it has nothing to do. In a way, it has nothing to do with my nice measure, my SLE loop measure, because I'm just defining operators on the space, acting on the space of Jordan curves. But this is not really specific to my measure, and so for that I need to change slightly my operators. And the modification I'm going to define now, this time, will satisfy the integration by parts formula I was after. Okay, so modification of LV. So LV like this of F. So we'll take. So this will be defined again for nice enough functions F, and to each Jordan curves eta. So it associates LV F of eta, so the one I had before, plus a correction, which depends on the central charge Cm. And now I have simply a multiplication. So I multiply F of eta by something that depends only on eta, but not on F anymore. But I'm not going to define. I'm not going to define it here because I think it will be a bit better for you. And so the result is that this time these operators they form a representation of the Virasoro algebra. And so okay. So I'm not going to. Okay. So basically, what this means is that they satisfy the following relation. So n minus m L n plus m, so the same I had before, plus a correction that depends on the central charge. Okay, so this is saying that it is a representation of the Virasoro algebra. Again, you don't need to know really what this means, but this means that it will be a very powerful tool. It has a lot of structure. These operators really have a lot of structures, and we'll be able to do many things with them. And what these operators now, they are very well suited to the measure nu, because basically what I'm going to say now is that if I consider the adjoint star is the adjoint for my L2 of nu inner product, I will simply get L minus n. So this will be my integration by parts. So I'm going to state this a bit more precisely because actually this equality is not true. Is not true like this. I need to modify it a bit. And this time, this thing depends very much on nu, because here I'm considering the adjoint with respect to L2 of nu. And going back to the picture I had over there, this will be the analog of the Gaussian integration by part. Okay. So actually, this relation will not be satisfied if I consider. So I need to define another Hermitian form, which is basically the inner product with respect to L2 of nu. But I need to introduce this theta operator, which exchange the roles. So exchange 0 and infinity. So basically, what I do is that I have my curve eta, and I'm just exchanging. I consider eta by exchanging 0 and infinity. And so the result is that. This time, this is true with this Hermitian form. So Q ln f g is equal to Q f l minus n g. For all, yes.
When you say Hermitian form, is like it is positive defined or?
No, so exactly. So I want to come to this point now.
You just think that it's not degenerate.
So the fact that it is non-degenerate is really clear. So you will need to see what theta really is. But so theta, what's important is that theta has two eigenvalues, +1 and -1. So the spectrum of theta is equal to plus or -1. And so, like on the subspace of functions where the eigenvalue is +1, you could call this the even functions if you want. And this will be this thing will be positive. So Q F will be positive, or at least non-negative for all f such that theta of f is equal to f. And it will be negative otherwise. Again on the space where theta is equal to minus f. The space of odd functions. So actually, this thing is not semi-positive definite. Which creates problems. So in the CFT language, this would be saying that we don't have a unitary theory. But okay. So now let's try to wrap up. I had a measure that satisfies this conformal restriction property. So from this conformal restriction property, I want to derive some sort of integration by parts formula, which is exactly what's written on this board over there. So this was not an easy task, because for that you first need to say what you mean by differentiating in your space and by considering really the appropriated operators. But okay, here it is. And from there you will keep going using some CFT techniques to build your orthogonal polynomials that will in the end you will be able to compute moments that are associated to these orthogonal polynomials, really in the same way as what I did here with the Gaussian group. And these polynomials, they will be dense in your space, so they will characterize everything. Okay, I'm going to stop here. Thank you.
Could you detail what is the small theta neutral of the?
Okay, so this is maybe the best. Okay, I could either give you the definition, or I could also tell you how you can guess the definition, which is maybe more interesting. So nu. So this is my SLE kappa loop measure, nu kappa, d eta. I'm going to compare it with a nu for kappa equals 1/3, which is the same as c equals 0. So you see, if c equals 0, I don't even need to introduce this second family of operators. I would have that already for my previous operators. And now I have a weight which is e to the cm over 12 maybe 24. And I have a term here which is the Loevner energy of the curve. So this, this is the path integral formulation for SLE, which is of course, which doesn't make sense because the two, they are not absolutely continuous. But from there, you can now start to, if you take, you can make formal computations from there and derive an integration by parts formula, really in the same way you would do for the Gaussian random variable, and you would end up differentiating the Loevner energy of eta. And if I differentiate my Loevner energy in the direction v, I will end up with a term that looks this term will be basically theta of V. That's how you guess. What to put over there for theta, and it will be. In the end, you will have the Schwarzian derivative of the uniformizing map of the exterior of the curve. Actually,
It's like a metallic LV applied to ELE.
I don't know. Okay, so that's how it is. Yes.
Maybe it's a related question. I don't know. I guess you wanted to have a notion of differentiating with respect to curves, but really what you did was kind of construct a flow of things.
Mm-hmm.
And I guess this wasn't obviously apparent in the. There wasn't a flow in the story on the real line.
Yeah.
But I guess the flow has something to do with the heat equation. I mean, it has something to do with.
So in the real line, I'm not so the problem is that here I can differentiate only in one direction.
Only in one direction, yes.
So I don't know what to say because also our notion of differentiation does not really depend very much on our initial measure. So, for instance, this result over there is really a general result about operators on acting on the space of Jordan curves.
So, if I were to start from an SLE loop measure and try to flow according, in some direction,
Mm-hmm.
what could you say? What's the evolution of this? What do we? Is this something that can be understood or described?
Absolutely. So we understand very well what's happening infinitesimally. Yeah.
Can you say, or this is what's described by this generator?
Yes. So this is what these equations that describe that.
There isn't a way to try to sort of send t to infinity and try to.
Sending t to infinity.
Might not even exist.
Yeah, exactly. At some point, my phi t is not even well defined.
Maybe it's slightly related, but so it goes back to the very first motivation of the talk. So starting with the discrete and then I guess taking scaling limit. So how explicit are those LV and L bar V in the sense that if you have, my question is, if you have a way of discretizing the operators and then checking that your discrete curve satisfies kind of discrete integration by part, how where can it get you to show kind of scaling limit results?
Okay. Yeah. So if this is your question. I'm pretty sure that it would be quite hard to use that to show scaling limit results. I don't think this would be useful in this context. Because already, this is quite a...
No, but because, for example, I don't know, for Ealing or for the GFF,
yeah.
You have operators that are like CFT operators that have been defined on lattices.
Yeah, exactly. So in these very special settings where already at the discrete level you have some sort of conformal invariance, maybe you could make sense of some of this in the discrete, but it's not clear.
So we said that given an unstable SRU, the outer boundary is a simple SRU. So given no conditional, given outer boundary of this non-stable.
So this, okay. So you're talking about the conditional law of white given purple.
Yeah, conditional given the outer boundary.
So this, okay. So this is a bit tricky. Okay, so I know much more the case kappa equals a3, because here, oh, okay, maybe no, disregard what I said. I was thinking about actually the conditional law of Brownian motion given its outer boundary, but it's a completely different story. So okay, so for this here, I don't know at all actually what's the conditional law of SLE kappa given its outer boundary, the non-simple setting. I don't know.
I had a second question, but I think go ahead. I've already asked a question.
Did you actually take it before?
No.
So, is that, I mean, given you have like L0 in the Hilbert space and everything, could you is there any way to calculate, like, say, a partition function like trace e to the minus constant L0, like some CFT partition function?
Yeah, so this is okay. So already, like the partition function of our model actually was computed by Shin-Sun and collaborators, and in this context, it's this corresponds to. Okay, so I have this would be my SLE loop, separating 0 from infinity. And I will condition on. Okay, so I have two natural notions of conformal radii. One of this domain seen from 0, and one of this domain seen from infinity. And if I condition on, let's say, this one being equal to 1, and I look at the conformal radius of this domain seen from 0, I take it to the power lambda. And I take the expectation of this thing. This turns out to be a notion of partition function in our setting. And this has been computed. So it's a very nice formula computed by Shin-Sun and collaborators. So yes, there are. I mean, okay. The short answer would be to say that yes, there are definitely nice quantities that you can compute. Here. And we actually hope to compute more using these techniques.
So, if I look at this Q here, that's still on the board, this Q of FG, can I think of this Q as endowing the space of maybe L2 of nu, or maybe the space of Jordan curve, I'm not sure, with some sort of complex structure, like some sort of Taylor structure?
Yes, so this I must say, I'm not sure exactly. First of all, I'm not sure what a Taylor structure is. So.
It's a way of complexifying, I guess. So you have your Lie algebra here, and which is the wheat, and you want to turn it into a complex, I guess, vector space. It's like, you know, when you want to define multiplication by I, when you want to rotate by 90 degrees.
I see.
You can also sort of decompose it. This is, you know, if you were to diagonalize the matrix corresponding to multiplication by I, there would also be a spectrum, you know. You can also see it as something where the spectrum on one component is +1, and one component is -1. It's very similar to that somehow. So
yeah, that's indeed possible. Yeah. But in any case, it does endow your Hilbert space L2 of nu with an additional structure. So that's yes, that's true.
I think it's probably closer to a real structure, rather than a complex one.
Okay.
In that this theta symbol corresponds to complex conjugation.
Yeah, it looks like complex conjugation.
More like complex conjugation rather than being like complexification. It's like more like realification. Because this is somehow related to, like, you're saying this also can swap the area of infinity, which also swaps the orientations of the curves, right?
Yeah.
I mean, isn't it this Weil-Petersen space story? I mean, this is pretty much like the Jordan curve.
Yeah, but okay. So this is very much related to this story here. this thing, I think, can be seen as a Kähler potential on something, and I must say I'm not sure exactly what this means. But indeed, there is this Loeffner energy here. It has a lot of structure that is related to what you're talking about, but Lin Wang would be the expert for this business.
Okay, let's thank Antoine again.